journey, we're going to be starting from the surface of the Earth, and we're going to go travel all the way to the edge of the solar system. In this journey, I'm going to split it into 6 stages, and each stage is going to be an order of magnitude larger than the previous stage. So our first stage is going to start on the surface of the Earth. We're going to look at the techniques we use to get to space around Earth. And then from there, we're going to further our reach to the moon. And we're going to keep going until we reach Venus and Mars, which are nearby planets. And then we're going to expand to include the entire solar system in our domain. And we're going to keep zooming out until we achieve interstellar travel. And then eventually we will start bending the laws of physics to travel intergalactic until we reach the absolute edge of the observable universe. But before we travel throughout the universe, it's very important that we start at Earth. So before a rocket even gets off the launch pad, there's a very important criteria that needs to be met. And this criteria is the thrust to weight ratio. So the thrust to weight ratio essentially is just thrust divided by the weight of the rocket, so mass times gravity. And if this ratio is below 1, then the rocket is heavier than the amount of thrust that it can produce, and it will stay on the ground, or if it's in the air, it will fall downwards. If the thrust to weight ratio is exactly 1, the launch vehicle will hover in the air. So it won't go up, it won't go down, it won't accelerate in any direction. And this is called gravity drag. We want to ideally reduce our gravity drag because our fuel is just being wasted doing no useful work, and we're just hovering in the air. But if our TWR is greater than 1, then we accelerate upwards and we move towards space. Now, normally rockets have a TWR between 1.2 and 1.5. The reason for this is because if our TWR is too close to 1, like I mentioned, we will experience gravity drag. And as a result, we'll waste a lot of fuel just hovering as opposed to flying upward. But if our TWR is too high, then we accelerate too quickly, and then we waste fuel fighting against atmospheric drag. Now, we know what TWR range we want to work with. We're now going to use that information to choose an engine. Usually engines or forms of propulsion have 2 specific quantities we look at, which is engine TWR, which is different from rocket TWR, and the specific impulse of an engine. So the engine TWR is essentially a proxy for measuring the sheer amount of force the engine can create, so the thrust the engine can create. And the specific impulse of the engine is analogous to measuring the fuel economy of the engine. The specific impulse is essentially a quantity that measures the number of seconds 1 pound of propellant can produce 1 pound of thrust. And an engine, usually you'll find engines with low ISPs and high TWRs, or high ISPs and low TWRs. Ideally, we want to use a high TWR engine on the ground, but once we're in space, we want to be using a high specific impulse engine because they're more fuel efficient. Now that we've decided and looked through the different kinds of engine properties we have, I wanted to run us through a few different examples of forms of propulsion we can use. The first and most common of them is the solid rocket booster. You'll find this on multiple rockets, most notably being the Space Shuttle and the Space Launch System, which is launching the Artemis spacecraft. The solid rocket booster is called the solid rocket booster because its fuel is solid. So other engines I'll show you run on liquid fuel or some form of liquid fuel, but the solid rocket booster is basically a controlled bomb that runs on solid fuel. Its vacuum ISP is 268 seconds, and it produces an insane amount of thrust, which is 14.7 million newtons of thrust. The only problem with solid rocket boosters is you can't control their thrust. So once you turn it on, it fires and it runs all the way until it runs out. So model rockets you would have seen also run on solid rocket fuel, and they provide 0 control authority. So they're really well suited to getting your rocket off the launch pad, but if you're in space and you want to maneuver around, they're not a great choice. Then we have the engines that complement solid rocket boosters on the launch pad. This is the Rocketdyne F1 engine. This is an older form of engine because it was used on the Saturn V rocket during the Apollo program. It uses a fuel called Kerolox, which is just liquid oxygen and kerosene. And as you can see, compared to the solid rocket booster, it doesn't provide a lot of thrust. Compared to 14.7 million newtons, we only have 6.77 million newtons, but we have a higher vacuum ISP. The reason this engine is a bit older and inefficient is because it uses an older design called an open cycle design. And newer engines that I'll show down the line use a closed cycle design. Another engine I wanted to include on the list was the SpaceX Merlin 1D engine. Now, of this entire list, arguably this is the engine that produces the least amount of thrust. It produces only 981,000 newtons, so not even a million newtons of thrust. However, it has the highest engine TWR, which means for its own weight, it produces a lot more thrust than other engines do, which means this engine can lift up to 200 times its own weight. And ultimately, the quantity we want to meet is TWR. So we don't always only look at the raw thrust figures. This is also an open cycle design and also runs on Keralox. Moving on to the engine that powered the space shuttles and the Artemis missions. This is the RS-25 engine. Five of these are found on the SLS, and 3 of these are found on the Space Shuttle Orbiter. It produces 2.2 million newtons of thrust, but it uses a different type of fuel, which is hydrolux, which is hydrogen and liquid oxygen. And it's extremely efficient because you get a lot of fuel economy out of using hydrogen. The only problem is hydrogen is not very dense. So to generate a significant amount of thrust, you need turbopumps to pump a lot of hydrogen at the same time to generate enough pressure in the combustion chamber to produce the required amounts of thrust. Last but not the least, we have the arguably the best of these engines, which is the SpaceX Raptor engine. This runs on a different kind of fuel, which is methalox, so methane, liquid methane, and liquid oxygen. It has a very high ISP, 380 seconds, and it also has a decent amount of thrust. The reason this engine uses methalox is because it is used on the Starship set of spacecraft, and the goal for Starship is to eventually land on Mars and accelerate interplanetary travel. So it is theorized that on Mars you can synthesize methane, and these engines are designed essentially for that purpose, so that you could send these spacecraft to Mars and then they could refuel over there. Okay, having chosen an engine from this list or other similar engines, we now have our rocket moving through the air. As we gain speed, we're going to also experience aerodynamic drag. There's 2 extremes to this. When our rocket's sitting on the launch pad, it has 0 velocity but maximum air density. And when our rocket's in space, it has maximum velocity and 0 air density. But between these 2 extremes, there comes a point where we have a decent amount of velocity, but the atmosphere is also still fairly thick. And as a result, that specific point is known as the point of maximum dynamic pressure, or max Q. Now, max Q wastes a lot of fuel because it increases the amount of aerodynamic stress on our vehicle as well, and it requires us to engineer a stronger rocket, and obviously we're wasting fuel in the atmosphere. The way to combat this is as we're approaching the theoretical max Q, we basically throttle down our engines so that we reach a constant dynamic pressure, which is much lower than max Q. And then once we've cleared the thicker parts of the atmosphere, we throttle our engines back up again, and all of a sudden we have saved a lot of fuel, and we've also saved our rocket from experiencing these great amounts of stress. Once we cross the 100-kilometer above sea level line, we are in internationally recognized space. Now, to get to orbit around the Earth, we need to have a high lateral velocity. We need to be moving sideways really quickly. But to clear the Earth's atmosphere, we need to be moving vertical really quickly, which is why our rocket's vertical on the launch pad. So between this vertical and horizontal position, there has to be a point where we turn the rocket and accelerate sideways and stop accelerating upwards. To do this very efficiently, we utilize what's called a gravity turn. Because we don't want to waste a lot of fuel with our engines turning left and right to essentially maneuver the spacecraft in a different direction, once the rocket has launched and cleared the launch tower, we essentially use a little bit of fuel and turn the engine a little bit so that the rocket turns 10 to 15 degrees against the vertical axis. And what this does is, as the rocket is accelerating upwards, gravity slowly starts pulling the nose down. So by the time you reach space, gravity will have pulled you basically perfectly horizontal. And this saves us a lot of fuel because we're minimizing steering loss. And as a result, we can accelerate quicker or carry less fuel and get the same amount of speed out of our rocket. Okay, once we've made it to space, it's important for us to sort of define the metrics with which we travel space both interplanetary space, interstellar space, and beyond. And this important metric is delta V. You can think of delta V as the currency of astrodynamics, simply because if you run out of delta V, you're stuck where you are in space. Delta V can be thought of um, as the cruising range indicator on your car. Obviously, each car is built different. It has different masses. It has different fuel tanks. It has different fuel types. It has different engine capacities. But all of those values can be translated into one single cruising range value. And a similar policy applies for rockets. You can have different size rockets, different engines, different fuel types, but all of that will eventually give you a flat delta V number. And that delta V just keeps going down as you burn fuel. And the reason this delta V value is so useful is because to get from any one point in space to any other point in space, the delta V requirement is fixed. It doesn't vary with the rocket you use or the type of mass you're sending. It's just a fixed value. Like I said, if we run out of delta V, we can't make any trajectory changes. So our velocity is stuck as it is. Now, delta V can actually be related to the mass of the rocket, the dry mass and the wet mass, using this equation. It's called the rocket equation. So m naught is the wet mass. Basically, our fully fueled rocket with all the fuel, all crew, everything on board. And then mf is our dry mass, which is essentially the rocket after it has run out of all fuel and can't turn on its engines or do any trajectory changes. This ratio is locked inside a natural logarithm, and it's multiplied by VE. And VE is the exhaust velocity, basically the speed at which exhaust is coming out of your engine. Now, because the mass ratio is locked inside a natural logarithm, if we need to double our delta V, aka if we need to travel, if we need to increase our cruising range to 2x, what it originally was, we need to square our mass ratio. And this is incredibly inefficient, obviously, because that means there is a limit to how big a rocket we can send. And as a result, most rockets are just 85 to 90% propellant by mass because of the essential natural logarithms effect. To further maximize the delta V, we want to reduce our dry mass. The way we do that is once we've burnt a bunch of fuels, burnt a bunch of fuel and got into space, we ditch the empty tanks, we ditch the old engines, and we move on to other engines and other fuel types in a process called staging. And this dead weight saves us fuel, and it allows us to squeeze out a bit more delta V from our rocket. This is an animation showing how drastically we reduce our rocket size. As you can see, this is the Saturn V rocket. It's just launched. The core stage is firing. The Rocketdyne F1 engines are firing at full power right now. They throttle down a little bit because of max Q, and then they throttle up. Eventually, the engine's expended, and we drop away that entire stage and that entire engine. So that's a bunch of tons we've just lost in dry mass. Then our second stage fires, and this puts our rocket into orbit around the Earth. And this burn lasts a lot longer because you have to have a very high lateral velocity. As this burn's completing, we're losing mass again because the fuel's being spent. And then after that, we ditch that tank as well. And we're left with our transfer stage, as well as the Apollo command module, lunar module, and service module. Then this burns, puts us on our trajectory to the moon. And eventually we're left with that little module that you can see from what was originally a huge stack of just fuel and explosives. Now, I just wanted to put some numbers to what I was saying. The delta V requirements to get to low Earth orbit, which is usually 400 kilometers around the Earth, is 9.5 kilometers per second. To get to polar orbit, it's 10 kilometers per second at the same altitude, because you need to, when we're launching a rocket, Earth's rotational momentum also adds to it. So if we're launching in an equatorial orbit, we can take advantage of that and save 500 meters per second. But if we're launching in a polar orbit, we need to cancel that out. So that costs us 10 kilometers per second. We can also go in a highly elliptical orbit. Now, depending on how elliptical your orbit is, this delta V figure can vary, but for the one I'm showing on screen, that's 12 kilometers per second. Finally, for the geostationary orbit, we have 13.5 kilometers per second. And that's geostationary orbit, as you know, is the orbit where our orbital period is the same as Earth's rotational period. So we only see one side of the Earth at all times. Now, if we're staging, we can also take advantage of the fact that we're moving from the atmospheric pressure at surface level to the vacuum of space above 100 kilometers altitude. And the way we take advantage of this is by increasing the size of our engine nozzle. The way this works is when exhaust is being released from our combustion chamber, the nozzle bell lets it expand. Now, at sea level, you have to let it expand only up till atmospheric pressure, because if you let it expand beyond that, atmospheric pressure will rush in and damage the engine. But if you're in space, you can squeeze out a lot more energy from that exhaust gas by letting it expand far more, and that effectively increases the ISP of the engine, because now for the same fuel, you are getting a lot more punch. And well, obviously the engine's expansion ratio increases. So for the SpaceX Merlin 1D, which I talked about earlier, the sea level variant has a speed of 311 seconds for an expansion ratio of 16:1. But the vacuum level variant, where the expansion ratio is more than 10 times that, 165:1, our ISP increases to 348. So our engine became more efficient because we're squeezing out more delta V from each specific amount of fuel that we have. Now, this is just a quick recap of what we've done so far. We're successfully in Earth orbit, but to get there, we've had to punch through the atmosphere. We had to talk about max Q. We had to talk about the gravity turn. We had to talk about staging. As you can see, the rocket has just staged. And then I talked about how long the orbital burn needs to be to place our rocket in orbit. And then eventually, because we've ditched our core stage, you will see the core stage eventually come into the atmosphere. It should come just any second now. All this time, you can see the engine is still burning on the rocket. And there we go. You can see it streaking through the atmosphere. And eventually now our rocket will be placed in orbit. Our little space probe will be placed in orbit. Now that we've placed it in orbit, the next destination obviously is the moon. Now, before we set a course for the moon, we need to look at climate control, because we're in the vacuum of space. So convection and conduction don't work. And as a result, if we had a spacecraft or even a planet without an atmosphere in space, the sun-facing side can bake at very high temperatures, up to 120 degrees, but the side not facing the sun can freeze down to negative 150 degrees Celsius. So we don't want to use thick insulation to protect our craft from this, because the thick insulation will be heavy and we already have a very restricted amount of mass. Remember, if we increase our mass, we decrease our delta V. So we use what is called multi-layer insulation. This essentially is the gold sheet you can see on the space probe I've shown, and it reflects 99% of the heat back into space, and it's basically microscopic layers sandwiched between each other. The problem with MLI is that internally generated heat is also reflected inwards and is stored, so it's essentially a little blanket. What do we do for that? We build a heat rejection system. Now, this heat rejection is done using the Stefan-Boltzmann law. Essentially, what we're doing is we're using the principles of radiation. We're having liquid ammonia be pumped through cold plates that are called radiators, and they radiate the heat from inside the craft into outer space. And then obviously that liquid ammonia flows back and it cools the craft from the inside. And obviously you can control that as you want to govern the internal temperature of your spacecraft or space probe. This is what a radiator panel looks like. You can see the white panels that are pointing downwards are the radiator panels, and the gold panels you can see are the solar panels. Okay, moving on. We can now look at the delta V requirements to get to the moon. As I mentioned, delta V is the currency we use in space. So to get from Earth to low Earth orbit, we need roughly 9.3 kilometers per second of delta V. To get from Earth on a trajectory that gets us to the moon, which is called a translunar injection, we need 3.1 kilometers. To actually capture in orbit around the moon, we need another 0.9. And to land on the moon, we need 1.9. I'm not even including the values to get from the moon back to the Earth, but you can see this the high amounts of delta V requirements we have just to get to the moon. Now, if we take some assumptions, let's say we assume our exhaust velocity to be 4.4 kilometers per second, we can get the mass ratios needed for different parts of our flight. So let's say we were starting on the surface of the Earth. If we wanted to send 1 ton of payload to the moon, then from the Earth, we need 30.6 tons of fuel for every 1 ton we're sending to the moon. But if we were starting in low Earth orbit, then we'd only need 2.9 tons. So again, it divides by 10. This is because we're on the surface of the Earth, we're deep within Earth's gravitational well, and we have the atmosphere. But in space, in around low Earth orbit, we already have a lot of velocity, and we're higher up in the gravity well of Earth. So we can exploit this to cheat the rocket equation, because like I mentioned, there comes a point where you can't send any more payload to low Earth orbit or beyond without requiring a second launch. So in this case, as you can see, the red curve signifies the mass equation as it grows for the amount of payload you want to send to the moon. And beyond 80 tons of payload, you just can't do it from Earth if you account for losses. However, if you launch two rockets, then the mass can be shared amongst them. And as a result, you are basically resetting the rocket equation, and your fuel requirements will be much lower, and you will save a lot of money. And this is the sort of guiding principle behind the Starship missions, because their goal is to launch the ship into orbit and then launch a tanker and then refuel. And from there, the refueled ship will then proceed to the moon or Mars. Okay, now that we have a fully fueled spaceship in low Earth orbit, how do we get to the moon? We need to learn how to extract the most amount of kinetic energy for the given amount of delta V we have. So we use what's called the Oberth effect. The Oberth effect can be split into two principles. The first one being changing our speed. So as you can see, I put up a changing kinetic energy equation on the slide. And for a high amount of V, in the first term, mv multiplied by delta V, if we have a higher velocity, then for the same amount of delta V that we expend, we're getting a much larger amount of kinetic energy. So if we want to increase the size of our orbit or speed up, then it's most efficient to speed up when we're at periapsis, because that's when we're fastest. And if we want to slow down, then it's very efficient to do that at periapsis as well, because then we'll be reducing our kinetic energy really, really. However, if we want to change the orbital inclination of our spacecraft, right? Let's say we want to go, we want to change from a equatorial orbit to a polar orbit, then we need to essentially cancel out all of our lateral velocity and then burn in a vertical direction to create new velocity, right? This logically is most efficient to do when we're moving the slowest, because we're essentially zeroing our velocity and then starting from scratch, essentially. So if we want to do this when our velocity is the lowest, then obviously we must do this at apoapsis, when we are highest and furthest away from the gravity well and we're moving at a very slow speed. Okay, now that we know those two top tips to save delta V in space, we come to the translunar injection, which is the maneuver we use to get from low Earth orbit onto an intersection with the moon. Every craft that goes to the moon performs this burn. And like I said, we need 3.1 kilometers per second of delta V for it, because our apoapsis, essentially the highest point in our orbit, changes from 200 kilometers to 400,000 kilometers. So it really becomes an elongated orbit. Now, we need to take a few things into consideration when we're performing a translunar injection. Number one, it takes 3 days to get to the moon using this burn, which means the moon in its orbit will have moved 60 degrees or 70 degrees along its orbital plane, which means we're not firing towards the moon. We're going to be firing to where we think the moon's going to be in those 3 days, in those 72 hours. And as a result, as you can imagine, the margin of error is very, very small, because if we mess up in our timing of the burn, if we mess up in the duration of the burn or the amount of delta V we've actually expended, we can end up missing the moon completely or end up crashing into the moon. Now, I want to mention a very specific type of TLI, and this is the free return trajectory. This is essentially a type of translunar injection burn that gets you on a path to intersect the moon, and then the moon will slingshot you back towards the Earth, such that you will land on Earth safely. The margin for error for this is even smaller, because now not only are you targeting a specific point in the lunar gravitational field, you're targeting a specific point of atmospheric entry on the Earth. The free return trajectory is very popular because it is a very safe trajectory. Let's say your engines fail when you're next to the moon. You can easily use the free return trajectory to get home for cheap. And the missions that have used this are the Apollo 8 missions and the Artemis 2 missions, which were testing out their systems for their respective series of missions. And the Apollo 13 mission also used the free return trajectory for when it had the mishap with its service module. Now that we've performed our TLI burn, we're slowly moving away from the Earth. And as we move away from the Earth, we have another hazard to worry about. And obviously, that hazard is the fact that we're leaving Earth's magnetosphere. So once we're leaving Earth's magnetosphere, we'll be exposed to all forms of solar radiation and cosmic radiation. But what's more dangerous is the part where we actually leave it, because the boundary stores a lot of high energy particles. The Van Allen belts, essentially, which are donut-shaped rings around the Earth, trap a bunch of the cosmic radiation and solar radiation that hit Earth's magnetosphere, and they create an area of higher radiation. So satellites in the Van Allen belts can suffer a lot of damage, as well as spacecraft, because both the electronics of the spacecraft as well as the crew on board can experience radiation exposure that can cause damage to, well, their health or the ship's health. Now, like I mentioned before, with the heating issue, shielding is not an option because we're trying to save on the mass we have. So the goal here is the TLI burn will be timed such that we basically punch through this layer, right? So we're not spending a lot of time at this boundary in the Van Allen belts, and we're saving ourselves, saving our lives, and this reduces the total amount of radiation we've received. Now, to save the electronic side of things, because obviously cosmic radiation can have the same effect that the Van Allen belts can have, we have 3 separate CPUs usually that run the same calculations at the same time, and they produce the same results. But let's say one CPU was struck by radiation, it would produce a different result. Then a voting system would take place, and then the winner of that vote will essentially be the calculation that's used. And in the background, you'll have an algorithm that's constantly scrubbing through your hard drive to make sure that no single event upsets have corrupted data on the drive. Okay. Now we reach a problem in orbital physics, and this is the 3-body problem. I'm sure many of you are familiar with it, but essentially the 3-body problem is mathematically chaotic. You can't predict where a craft will go very, very accurately using algebra for 3 specific bodies, where the 3 bodies would be the Earth, the Moon, and the spacecraft itself. You can do it very easily for 2 bodies, say the Earth and spacecraft, or the spacecraft and the Moon, but you can't do it for 3 bodies. So what modern computers do is they brute force it, right? They run the numerical integration step by step until they get the entire trajectory to the Moon. But back in the day when we sent the Apollo missions, we had to use a different method because the Apollo computers were as powerful as the smartwatch on your wrist. This method is called the patch-conics approximation. So how does this work? Well, between these 2 bodies, the larger bodies, the Earth and the Moon, we define a boundary, and we say that boundary is the sphere of influence. And if we're in Earth's sphere of influence, we ignore the Moon completely, and we perform our calculations pretending it's a 2-body problem between the Earth and the Moon, between the Earth and the spacecraft, and that makes our life a lot easier. And then once we cross that boundary and the Moon is exerting a stronger pull on us, we consider the Moon and we forget the Earth. And then once we plotted these 2 parts, we essentially connect them at the boundary. And that's why they're called patched conics. The reason they're called conics, as some of you will know, is because the parts traced out, parabolas, ellipses, hyperbolas, they are conics. Okay, but how do we define where this sphere of influence boundary actually lies, mathematically speaking? Well, I've put the equation there for you. If you run the numbers and for the Earth and the Moon, you'll find that the Moon's SOI is 66,100 kilometers from the center of the Moon, not from the surface, from the center of the Moon. Now, as you can see, the path in the Moon's sphere of influence looks like a hyperbola, and I've cut out the path around the Earth, which is the blue path, but essentially that looks like an ellipse. Now, obviously, as we enter a sphere of influence, because we're changing bodies of reference, we need some way to carry over the velocity we're moving with, and that's called hyperbolic excess velocity. Essentially, this is the velocity we come in the SOI with and also leave the SOI with. Okay, that's an approximation we used, but in real life, we know that gravity is not a switch that flips between the most powerful body acting on us. At any point in time, we'll have the Earth acting on us, the sun acting on us, the moon acting on us, which is also why we have tides on Earth, right? Because the moon's gravity acts on the Earth, even though we're not in its SOI, so to speak. This results in some interesting geometries where you have specific points in these two body systems that are gravitationally neutral in the sense that you can place a spacecraft in orbit around those points, and they're essentially points where the gravitational pull from two bodies is equal. There are 5 points. L1 is located behind the large body, right? Behind both bodies. So, and then you have L2, which is located behind the smaller body. You have L3, which is located behind the larger body. And then you have L4 and L5, which are 60 degrees ahead and 60 degrees behind the smaller body in its orbit. So if you look carefully, L3, L4, and L5 form an equilateral triangle in the circular orbit of the second body compared to the first. An important point to note is that these points are useful for instance, telescopes. So the James Webb Space Telescope sits behind the Earth, which allows it to be shielded from the sun's heat. And another point to note is that L4 and L5 are gravity traps, obviously because of the properties of the way they are. And for stronger planets like Jupiter, they've accumulated a lot of asteroids in those two traps, and those sets of asteroids are called the Trojans. So just a quick review for what we've done so far. Well, we looked at the Van Allen belts. We looked at the Obert effect and how you can burn at periapsis to raise your apoapsis really efficiently. Then we looked at the translunar injection burn, which is the burn you use to get to the moon. We talked about how you need to lead your shots, and we talked about the 3-day journey. Then we talked about the free return trajectory, which the Artemis 2 crew used, where they slingshot around the moon. It looks like a figure 8, and they head back home. We talked about the patch conics approximation, but we also talked about how modern supercomputers just brute force it as opposed to approximating it. Now that we've explored the Earth system, it's finally time to leave the Earth's sphere of influence and head towards our nearby planets. Before we do that, though, we need a metric for knowing where up, down, left, right, forward, backwards is, because we no longer have that now that we're so far away from the Earth. So in spaceflight, the 6 directions of thrust are prograde, retrograde, radial in and out, and normal and anti-normal. Prograde is burning in the direction you're traveling in. So it's like me accelerating, increasing my speed. Retrograde is the exact opposite of that. So I'm decreasing my speed. So I'm burning against my direction of travel. Radial in and radial out are essentially burning towards the center of the planet and away from the planet. And normal and anti-normal are burning, well, at a 90-degree angle from both the prograde and radial in. And you can obtain it using the cross product. And normal and anti-normal are used to perform plane changes, like I showed earlier. And prograde and retrograde are obviously to change the height of your orbit, or to break free from an orbit, or land on a planet, obviously. Okay, so how do we become interplanetary? Well, it depends on where we want to go. See, the Earth is moving around the sun at 30 kilometers per second. So if we want to go to a planet like Mars, which is higher in the orbit, we need to add our velocity to that. So we need to burn prograde relative to the Earth. So essentially, we need to add 2.9 kilometers per second of speed in the direct, and leave Earth's SOI in the direction of Earth's travel. But if we're going to Venus, we need to technically slow down. So we point the opposite way, and our hyperbolic excess velocity should then be 2.5 kilometers per second, so that it subtracts from Earth's 30 kilometers per second, and we can lower down to the Venusian orbit. Obviously, you can see how the Obert effect plays a role here, because you can't simply add what hyperbolic excess velocity you need to the delta V to get there, because of the efficiency gain you have when you're burning from, let's say, low lunar orbit or low Earth orbit. Now, how do I know when to burn? See, when we talked about going to the moon, it was easy. We talked about how long it takes to get there, and from there we deduced how much the moon would move, and then we figured out how much we need to lead our shot by. But the Earth and Venus, or the Earth and Mars, are constantly moving around the sun, and they're always at different positions from each other. So how do we know what the most efficient way is to get from one planet to another? Well, that method is the Hoffman transfer. The Hoffman transfer, because of Keplerian motion, the Hoffman transfer is going to be a half ellipse because whilst we're moving between these two planets, we're technically moving in a path around the sun. And a lot of complex math essentially happens, and we find that the Hoffman transfer can only happen, which is the most efficient way to go from these planets, by the way, can only happen between the Earth and Mars, for instance, if Earth is 44 degrees behind Mars. And for Venus, it can happen if Earth is 50, that many degrees. If Earth is essentially ahead of Mars, so 54 degrees ahead of Venus and 44 degrees behind Mars for the Hoffman transfer to take place. Now, in interplanetary space, the three-body problem worsens to the n-body problem. The three-body problem was solved using the patch-Conics approximation because we just ignored one body and looked at the other. But when you're in the middle of nowhere in interplanetary space, Earth is a small dot in one direction, Venus is a small dot in the other, Mars is a dot in that direction, Jupiter in that direction, and the sun is visible. They're all exerting a roughly same order of magnitude amount of force on you, right? So you can't ignore all of these bodies anymore, right? So you can't look at it as a two-body system, as a two-planet system where you can use the patch-Conics approximation. So now, for that to happen, there is no algebraic solution so far, and as a result, the only way to do it is computers have to brute force this method. So they'll calculate where the spacecraft will be a microsecond later, then look at all the forces and calculate where it'll be a microsecond later, and repeatedly do this for the 259-day time it takes to get from the Earth to Mars. The problem is, because we're estimating to some sense, right? We're skipping ahead a microsecond or a second in an interval. Eventually, those minute errors add up, and we could end up missing the planet by a bunch. So the way we fix this is make course correction burns. So maybe halfway through our travel, we'll look at where we are and where we thought we'd be, and then use that, recalculate, and then decide how much we want to course correct by. But that leads to a problem. How do we know where you are when everything around you is just a bunch of white dots on a black plane and you have the sun in one direction? Well, you use a camera, and that camera can look at the background stars, so away from the sun, and from that, it will know which direction it's facing, right? And once you know which direction you're facing, you can use flywheels and the conservation of angular momentum to correct where you want to be, where you want to look at, so that you can point prograde, retrograde, radial in, radial out, any along those 6 axes of directions of thrust. And then you can perform your course correction burn. But how do you know how far you are along your orbit around the sun? Well, you can use the speed of light. So you can look at the delay between a signal being sent from Earth and Earth receiving that signal back as a rough estimation. But you can also triangulate. So essentially, you do that for Earth, you do that for another spacecraft, maybe on Mars, and from that you can have 2 points to precisely determine where in space you are, and then you can have NASA supercomputers perform the recalculations of your course correction burn, and you can repeat this maybe 2 or 3 times throughout your journey. These burns don't cost a lot of delta V at all because you're basically threading the needle here. So you're really just rotating a tiny bit. You're burning a tiny bit to fix your trajectory a tiny bit. Okay, 9 months later, we are on arrival to Mars. Now, let's say we are an orbiter and we want to orbit Mars to perform science. How do we do that? Well, there's 2 methods, and the second method has 2 different ways of doing it. The first method is brute force, propulsive orbit insertion, where you burn retrograde, like I said, at periapsis because of the Oberth effect. You burn retrograde and you decrease your hyperbolic excess velocity all the way down to 0. And then you'll be placed in an orbit around the planet, which is an elliptical orbit, and then you can adjust the orbital height using the Oberth effect as you want to. Problem is, this costs a lot of delta V because you're canceling out all the velocity you're coming with, pretty much all the velocity coming with, leaving maybe the 4 or 5 kilometers per second you need to orbit Mars. The second method is using air resistance. Earlier in my talk, I mentioned how air resistance is a problem when I was talking about dynamic pressure, a dynamic maximum pressure. But in this case, we can use it to our advantage. Well, here's how we do it. Instead of approaching the planet at a random altitude, you approach it at a very specific altitude, which sort of dips into the atmosphere. So you'll have a tiny amount of air density to act on you. and that aerodynamic drag will then slow you down and bleed off that 1.5 to 3 kilometers per second of delta V. The problem here is obviously you have to be very, very careful because this is one pass. You get only one pass through the atmosphere, and you have to burn off pretty much all of your excess velocity. And then once you're at apoapsis, you can raise your periapsis above the atmosphere so you don't dip in the atmosphere and continuously slow down. Obviously, the problem here is you need to be very careful because if you overshoot, let's say you dip too far low, your orbital height could be reduced too much, or you could end up crashing into the planet. Or if you don't dip enough, you will end up flying off into deep space or being placed in an orbit that you never wanted and you can't correct because you don't have enough delta V. The second method is to do the same thing, but do it multiple times. So instead of one burn one pass that essentially slows you down a lot, you have multiple passes that slow you down a little at a time. And this method has actually been used by the Mars Reconnaissance Orbiter. So once you arrive to Mars, you burn retrograde, capture into an orbit maybe, using your engines. And then after that, you do slow passes through the atmosphere. In the case of MRO, it was 445 orbits over a span of 5 months. So you can see how slow this process is, but it's also safe. And you can reduce your orbit. And then after that, once you're done, you obviously correct your orbit to make sure you don't dip into the atmosphere continuously. This allowed the MRO to save 450 kilograms of propellant. And in place of that 450 kilograms of propellant, we put 450 kilograms of science equipment. Just try imagine how much 450 kilograms of science equipment really is. Okay, let's say we don't want to be placing ourselves in orbit. We want to land on the planet. We've sent rovers to Mars. We've sent landers to Venus. How do we do it, right? Well, I'm going to take the example of Mars in this case because it's a very interesting case. Look, this is the entry, descent, and landing curve for the Curiosity rover. I'm sure most of you know it. There's a similar curve for the Perseverance rover, but for the sake of an example, I'm taking the Curiosity rover. Rovers like these usually have a hyperbolic excess velocity of, well, not hyperbolic excess velocity. They enter the atmosphere at 5.5 kilometers per second, which you can see on the right. And we have a family of curves. So let's say we undershot, which is we didn't dip into the atmosphere enough. Well, those are the blue curves. You essentially fly back out of the atmosphere. But let's say we enter the atmosphere too much, right? Our angle of attack was too steep. Well, two things will happen. Either we will reach the ground so quickly that the atmosphere won't be able to slow us down and we'll crash, or the amount of G-forces on the rover will be so high that it essentially damages itself. Then there's the green family of curves, which you can see start off at a very, very tiny margin of error, and they obviously let you bleed off most of your velocity and still have enough time to deploy a parachute and do the other steps in landing on Mars. So we have about a 5-degree corridor of entry, and we use that to bleed 90% off of our speed. Now, we're still moving supersonic, right? We've slowed down a bunch. We've bled 90% of our speed, but we're still supersonic. We're at Mach 2. So we deploy a parachute, which withstands almost 300 kilonewtons of force, and it's designed to do that, and it slows the craft down to 200 miles per hour. This is the reason I took the example of the Martian atmosphere. The Martian atmosphere is thick enough for you to actually burn up on re-entry, which is why we had that entry corridor, but it's too thin for you to only perform a parachute assisted landing. So it's unlike Earth, where you can just land on your parachutes, or unlike the moon, where you can just land on your engines. On Mars, you have to do both. Now, the way this is done is after the parachute slows you down further, you're going to separate your back shell. You're going to take a look at the surface. The rover is going to image the surface. And then from there, it's going to perform a powered descent on what is called a sky crane. And this is what it looks like. It's called the 7 minutes of terror because the entire process from the 125 kilometer mark at the start of the atmosphere all the way to touchdown on Mars, it takes 7 minutes, and it is fully autonomous because the speed of light is confined, so we can't really do it live. You can see the rover is entering the atmosphere. It constantly fires its thrusters because unlike an orbiter that can orbit the planet with a little bit of give, the rover needs to land at a very specific spot on Mars, and the margin of error is much, much smaller. You can see the rover sustaining a lot of G-forces as we're entering, but it is within operational bounds. So it continues its descent. It's slowed down enough, and now it deploys its parachute. The supersonic parachute slows us down a lot, and now our heat shield will eventually have no use because we've bled most of that velocity, and air resistance isn't that big of a deal now. From there, we then drop the heat shield, which allows the rover to actually get a good look at the surface. And as you're looking at the surface, you're going to image that against what you have. You're going to say, okay, I need to move left, right, and the sky crane will essentially calculate all of that, and then it will fire its engines and will maneuver left or right based on how inaccurate our atmospheric entry was. From there, it will complete the descent all the way down to the ground. It will let the rover be tethered down, because otherwise the engines would kick up too much dust on the rover, and that would damage the rover as well. And from there, you're going to have nylon threads that essentially snap, and the sky crane moves out of the way and crashes safe into the distance. So you can sort of see the challenges associated to get just to Mars. And this is a rover. We're not sending any humans yet. And you can see how difficult the process is already. So I hope you get a bit of an appreciation for how this works. Finally, for this section, I wanted to talk about another form of transfer. I talked about the Hoffman transfer being the most efficient, but if let's say I'm traveling from Mercury all the way to Jupiter's orbit, that is a huge height to cover for our Hoffman transfer, which increases the delta V requirements. This is where the bi-elliptic transfer comes in. Essentially, the bi-elliptic transfer is taking advantage of the orbit effect. We're starting off by actually lowering our orbit, so we're closer to the sun. And then from there, because we're close to the sun, we're going to be moving much faster. We use that to increase our apoapsis all the way up to Jupiter. And then at Jupiter, we then circularize and capture into orbit. So that's 3 burns. The blue curve shows the Hoffman transfer. The red curve shows bi-elliptic transfer. And as you can see, it only is more efficient, and not by much even, if the ratio of orbital radii is greater than 12. So even though you can have an orbital radii difference greater than 12, your Hoffman transfer is still fairly efficient. Your bi-elliptic transfer is not going to be much more efficient. And in reality, we don't even use any of these methods for such incredible distances. We have other methods that I'm going to talk about in the next section of this talk, which segues me perfectly into the outer planets. Okay, starting off, Jupiter's orbit sits 5 times higher than Earth's orbit, right? It's at 5 AU. Now, all the way up to Saturn's orbit, which is the second of the 4 outer planets, solar radiance is only 1%. It's actually 0.7% of the power you receive on Earth. So you can't use solar panels, because the solar panels you need to generate enough power would actually be huge. So instead, we use a different form of power, and this is the RTG, or the radioisotope thermoelectric generator. It relies on the decay of plutonium-238, and that generates a lot of heat. And that thermal energy is compared against the cold vacuum of space, and that leads to a constant flow of electrons, which leads to a steady DC voltage. As is the case with nuclear fuel, it decays because it has a half-life, so that DC voltage slowly starts to decrease over the duration of the mission, and as a result, output power would decrease. So in later stages of the mission, you'd need to turn off a few instruments on your spacecraft to keep it running. But this is independent of the sun and independent of the distance you're traveling from the sun. The second thing is, once you're so far from the Earth, how do you communicate with the Earth? In the case of Voyager's high gain antenna, which is on screen, sends a 20-watt signal pointed at Earth. Firstly, like I mentioned when I was talking about attitude determination, if we miss our target angle by a fraction of a degree, we're going to miss the Earth by millions of kilometers. So our signal won't actually reach Earth, and Earth will think the craft is, well, done for. The second problem is our 20-watt signal. By the time it gets to the other side of the solar system, to Earth, its power will be on the scale of attowatts, 10 to the minus 18 watts. How do you detect that level of power for a signal? Well, it becomes a signal to noise ratio problem. So NASA has built 3 large dishes, 70-meter large dishes that are super cooled, that are 120 degrees apart from each other because the Earth rotates. So we want one to point in that direction at all times. And this is super cool so that the copper and physical materials used in the dish are basically stationary, almost stationary, because they have been robbed of all their heat energy, all their kinetic energy. And that means we have no ambient noise coming from that heat, and we can then receive this signal. The data rate, depending on where you are in space, can vary from 10 bits per second to 100 megabits per second. So let's say you're on the moon or you're on Mars, then you can leverage the deep space network at high speeds where you could even stream like proper video. But if you're all the way out as far as Voyager is, even writing a single line of code that will execute a command will take probably a few minutes to actually send, and then you'll have that speed of light delay between actually knowing if it was sent or not. Okay, those two problems aside, let's explore the 4 outer planets and beyond. Here are the delta V requirements. These are delta V requirements from low Earth orbit. If you want to fly by these planets, you can see what the delta V requirements are. If you want to fly by and then capture in orbit around these planets, because that also requires a bunch of delta V, you can see what those are, and you can see the total to actually get to orbit from low Earth orbit. 17.5 kilometers per second, 14.7. These are really, really high values from low Earth orbit. So the rocket you'd need would essentially be the size of a skyscraper, even if you did orbital refueling. And we can't sustainably do this, right? If we take the most powerful rockets we have today, the SLS Block 1B, and we take these delta V values and plug them into the SLS Block 1B to get the maximum payload it can send to these planets, well, you can have a lot of mass flyby. You can have 7.5 tons fly by Jupiter. You can have 1.2 tons fly by Pluto. But none of these situations will let you actually place a craft in orbit around these planets, which means Hoffman transfers are no longer an option. The other reason we can't use aero capture to capture in orbit and save delta V is because these are gas giants. They have very violent, very turbulent atmospheres. In the case of Saturn, it has rings. So we don't want to actually just damage our craft because its orbit was reduced too much and it's just stuck in the rings. So in theory, if we were to use the Hoffman transfer with our current technology, we're locked out of the outer solar system. But in reality, that's not true. These are a few crafts we've sent to these planets. We've sent 6 tons to Jupiter orbit. We've sent 5.7 tons to Saturn's orbit. And we've sent the Voyager space probes to fly by all these gas giants. And obviously, New Horizons flew by Pluto. Now, well, how did we do this? Firstly, another thing I want to point out is even though Voyager only flew by these planets and technically is within the theoretical limit, it reached Neptune in 12 years instead of 30. The Hoffman transfer would take you 30 years to get to Neptune, but we got there in 12 years. Well, clearly there's some other trick we're using, and that trick is called a gravitational slingshot. So a common theme here is in the very start of the talk, I mentioned gravity and I also mentioned air resistance being a problem. But in later stages of this talk, I'm mentioning how it's actually an advantage. So we use gravity to our advantage in this case. And what we're doing is we're stealing momentum from the planet. So depending on how you approach the planet, you can perform a flyby of the planet and you're going to leave with the same amount of velocity, well, speed, but your velocity will be in a different direction. And as a result, you will have essentially gained a bunch of speed because the planet would have dragged you along. Its gravity will have dragged you along. The speed is effectively free because the planets are so large that even if you had the largest possible payload you could send on a gravity assist, the momentum lost by the speed lost by the planet is going to be so small that even NASA doesn't consider it when it's calculating gravity assists. Okay, so gravity assists being the key, how do we use them? Well, we can use gravity assists to speed up, to slow down, or to change our plane of orbit. These are the three expenses I talked about in delta V. The green curve is how you speed up. You essentially approach from behind the planet and it pulls you along with it. The red curve is how you slow down. You approach in front of the planet and it pulls you backwards in a retrograde way. And if you want to plane change, depending on how you want to plane change, you can approach above the planet or below the planet and it will change your plane. Okay, knowing that we have gravity assists as the key to the outer solar system, how do we use it? Let's take the example of the Cassini-Huygens probe. This was 5.7 tons we sent to Saturn's orbit. And here I have a running balance for what the delta V was of the probe once it was separated from its rocket. So initially, the rocket actually put it on a flyby of Venus, which is inward as opposed to outward. And this Venus flyby added 7 kilometers per second of speed to the Cassini probe, which means we saved 7 kilometers per second of delta V. Then we performed a small maneuver so that we fly by Venus again, and that cost us 0.5 kilometer a second, very small stuff. And then we flew by Venus again, and then we flew by Earth, and then we flew by Jupiter, and then eventually we got to Saturn a while later. And as you can see, we started off with 2.4 kilometers per second of delta V in the tank, and we ended up with 1.33. So we saved almost 20 kilometers per second of delta V in getting to Saturn. And what do you do with 1.3 kilometers per second of delta V when you arrive at a planet like Saturn? Well, you do this. This is affectionately known as the ball of yarn. This is essentially a trace of the entire path the Cassini-Huygens spacecraft took throughout its life orbiting Saturn. You can see it's done really chaotic stuff. And another thing I want to point out is you don't have to only use gravity assists around planets. Because Saturn has so many moons, you can perform a gravity assist around one of Saturn's moons to maybe change your orbit to see a different part of Saturn, or actually capture into orbit, assisted with your engines. So the different colors you see are actually for different stages of the Cassini mission, because it lasted much longer than they thought it would. And this final stage was called the grand finale, and this used a series of Titan flybys to adjust its trajectory. Well, another example I want to take of gravity assists is a different realm of how we use them. With Cassini, we used it to save delta V. With the Voyager probes, we used it to save time. I mentioned that a 30-year trip was completed in 12 years by the Voyager probes, and this is because it basically hop, skipped, and jumped across the outer planets. It flew by Jupiter, then it flew by Saturn, then it flew by Uranus, and it flew by Neptune, taking advantage of this 1 in 175-year alignment that made it possible to do this. And both probes are interstellar now, and they move at 17 kilometers per second. And this segues me into the next section of my talk, which is interstellar scales, because even at 17 kilometers per second, it will take these crafts 73,000 years to get to our nearest star. Now, just to drill in the sort of distances involved with interstellar space, if the Earth and Sun were 1 inch apart, so essentially if 1 inch was 1 astronomical unit, Proxima Centauri, which is the nearest star, would be 4.2 miles away, right? So now that we're considering interstellar travel, we abandon the idea of delta V. We abandon the idea of efficiency. The only thing we want to be efficient in is time, not mass. We can send any amount of mass. The point is time. Our problem is time, because the delta V requirement becomes astronomical. We need 60,000 kilometers per second of delta V, whilst we're barely fighting for like 40 or 30 kilometers per second just to get to Alpha Centauri in a human lifetime. So chemical rockets, we're abandoning chemical rockets, we're abandoning our old rocket equations, because we're abandoning our old engines, because the specific impulses I was talking about, they're on the order of hundreds of seconds. But here we need burns that last years. The other thing I want to point out is the dangers in interstellar space. Look, we think it's a vacuum, and it is a vacuum in the sense that it is a better vacuum than the ones we often produce on Earth in most cases. But if you're traveling at the speed at a specific percentage of the speed of light that is greater than 1%, you are going to experience some form of drag because of what's in the interstellar medium. Essentially, as you can see, the red stuff here is interstellar gas, so that's 99%. And then the highlighted dots that you'll see in a bit, these dots, that makes up 1% of the interstellar medium, and that's just microscopic particles like dust and carbon and silicates. And the reason I say this is a really good vacuum, even though we have this interstellar dust and gas, is because the density here is 1 atom per cubic centimeter, whereas the atmospheric density on Earth is 10 to the power 19 molecules per cubic centimeter. So moving at classical speed, so the 17 kilometers per second of Voyager, doesn't make a difference. But if we're moving at a significant fraction of the speed of light, these particles essentially become high energy rays that slam into our craft, and they'll either provide enough ionizing radiation to kill the crew and damage our electronics, or they'll physically start shredding off our craft. Okay, let's assume we managed to mitigate the issue of the interstellar medium. How do we actually cross these humongous distances without dying along the way? Well, we use the brachistochrone transfer. The brachistochrone transfer, which is a mouthful, is also a bit of a misnomer in this case, because this trajectory is actually called the continuous thrust kinematic trajectory. What this does is, let's say my distance from one star to another is 4 light years. For the first 2 light years, my engines are going to be constantly burning at full power, producing 1 g of acceleration, or a specific amount of constant acceleration, and that constantly speeds me up, right? I'm just not going at a constant velocity. I'm just constantly accelerating. And then halfway through that, I will turn my engine around, turn my spacecraft around, burn retrograde for the rest of the half. So I spent the first half of my journey speeding up, and then it'll be the same process slowing down. Now, you can do that, or you can have a cruise phase where you speed up for, let's say, 25% of your journey. You cruise at a velocity for 50% of your journey, and the last 25% you slow down, right? It's going to be symmetrical regardless, and that's the sort of defining property of this transfer. Now, if we're traveling or cruising at a significant portion of the speed of light, classical physics becomes obsolete, and we now talk about relativistic physics. So a factor we're now governed by is called the Lorentz factor, and you can see its equation right here. So V is the speed we're actually moving at, C is the speed of light, and from that we can compute the Lorentz factor. So if we were moving at 0.9% the speed of light, so 0.9 C, the C's cancel, we're just left with 1 minus 0.9 squared. You evaluate that, you get gamma or the equals 2.29. And this defines the observational gap between Earth and the ship. So at classical speeds, T Earth equals T ship. So if I'm spending 1 year on the Earth, I'm spending 1 year on the ship. But if I'm moving at 0.9 C, if I'm spending 1 year on the Earth, if I'm spending 1 year on the ship, it's the equivalent of 2.29 years passing on the Earth, because we're multiplying it by the Lorentz factor, which in this case is 2.29. A similar adjustment needs to be done for our momentum, as well as our kinetic energy, and as well as our rocket equation, actually. So now, if we were to be ever worried about our mass ratio, this is where that would come in. The problem here is, again, like I mentioned, huge amounts of delta V. But if we have, at these speeds, if we have even a single gram of interstellar dust colliding with us, like I mentioned, is the equivalent of detonating 36 kilotons worth of nuclear warheads on the craft, right? So there's no difference between me just dumping a lot of nuclear bombs on the craft versus actually sending it into interstellar space. Now, I want us to look at this from 2 frames of reference. We have the Earth's and then we have the ship's frame of reference. So firstly, from Earth's frame of reference, what do we see? If I see a ship cruising by at 0.9 C, what do I experience? Well, for me, it looks like the craft is slowed down and is moving in slow motion. And obviously, like I said, 2.29 years on Earth is 1 year on the ship. From my point of view, as I look at the ship constantly accelerating, I see it get closer to the speed of light, but never cross it. So it'll be 90% of the speed of light, then 99%, then 99.99, then 99.9999, but it will never reach the speed of light. The other effect I will notice is if I'm receiving signals from the craft will be sending a signal, but because of its speed, it's going to be Doppler shifted. By the time I get it, a radio signal the craft sent will be in deep infrared. So I won't be able to read it very easily. So apart from the issue of attenuation that I mentioned earlier with the power of the signal dropping, we also have the signal being shifted into a completely different form of light, and that makes it even harder to detect. Now, for the ship's reference, we don't notice the slowdown of time. We don't notice the speed capping out or plateauing at the speed of light. For us, we're just constantly accelerating. I want to note that even in any frame of reference, we never break the speed of light. So from the ship's point of view, instead of us speeding up to the speed of light, what we notice is the physical distance shrinking down. So the same example of 0.9 C, if we're traveling to a star that's 10 light years away, it feels like it's 4.6 light years away. Like if we look out of our window, that's what it looks like. And because we're traveling at 0.9 C, if the distance feels like 4.36 light years, we can divide by 0.9 to get the actual traversal time, which is 4.8 years. And you can then obviously multiply this 4.8, which is the ship's experience, by 2.29 to get the speed, the time that would have passed on Earth. Now, in this time, the craft experiences heavy blue shifting. All the light in front of them is compressed into X-rays, gamma rays, and it's being blasted at them. And the closer you get to the speed of light, the more exaggerated this effect is. The second issue is, like I said, this 4.8 can be multiplied by 2.29 to get the time that would have passed on Earth, which means if I were to travel to another side of the galaxy, which is 100 million light years away, for instance, right, using this method, for me, maybe I'd get there in 5 years. But because of the Lorentz factor, Earth will have experienced a million years. So I won't even have anything. I won't even have a civilization to send back these signals to. Uh, so essentially, it's a one-way trip, right? You can't come back. Okay, this is a ship's point of view if you were accelerating beyond up to the speed of light. So you can see the center becomes blue because the center is blue shifting. You have motion blur from the sides. Eventually, everything shifts beyond your view. So like visible light. So everything compresses and you only see that high intensity X-ray, gamma ray coming from directly where you are. And then once you start slowing down, your normal effects return, which is your blue shifting, your field of view is expanded again until you perfectly slow down and you're in a new part of the galaxy. Okay, I talked a lot about traveling close to the speed of light, so I figured I had to include this. I'm sure most of you have watched the movie The Project Hail Mary, or at least read the book. This involves a craft called the Hail Mary, which uses astrophage to propel its craft. And if you run the numbers, the ISP of this engine will be 30.5 million seconds, which is insane compared to our hundreds of seconds. It uses a brachistochrone trajectory to get to the Tau Ceti system using a constant acceleration of 1.5 g compared to the 1 g example I gave you. And this ship's maximum cruising speed was 93% the speed of light. So if you run the numbers, a 4-year trip on the ship is equivalent to a 12-year wait on Earth. Now, we don't have astrophage, but have we ever come up with an idea similar to this? Yes, we have. In the 1970s, we came up with this project, which essentially uses an inertial confinement engine to accelerate up to 12% of the speed of light. So compared to the 93% of the speed of light we're talking about with the Hail Mary, this craft only manages 12%. And even to do that 12%, we need 50,000 tons of fuel, right? So with that 50,000 tons of fuel, we'll be able to travel 6 light years in 50 years, in a span of 50 years, because 12%. The problem is, not only is it 50,000 tons of fuel, it's 50,000 tons of rare elements. So we need heavy hydrogen and helium-3 to actually synthesize inside this. And they burn at an insane amount of insane temperature, which is 100 million degrees. So we can't use conventional nozzles. We use what is called a magnetic nozzle. Essentially, this is like a wire frame that has superconducting magnets inside it. So as the exhaust comes out, because the exhaust will have a charge, you can use that. You can use the magnets to essentially point the exhaust gas in the other direction, which propels you forward. The other thing I want to point out is because this craft is, well, even with this 50,000 tons of fuel, this craft will fly by the destination star system, which is 50 light years away, but it won't have enough delta V to stop. If you needed that delta V to stop, you need to square the mass, which means you get 50,000 square tons of fuel plus whatever the mass of the actual craft was. You can see how insane these figures are. Okay, moving on. Antimatter catalysis. This is the other way to do it. Inertial confinement fusion only converts 1% of your fuel's mass to energy. But if you want to do 100% similar to astrophage, you use antimatter. The problem is with our magnetic nozzles, which you can see here, antimatter creates high energy gamma rays, which is photons, and they're not electrically charged. So you can't really steer them with magnetic nozzles. The solution is to use a pion drive. So instead of colliding electrons and positrons, you collide protons and antiprotons. And for a brief moment after the collision, they produce charged particles, which are called pions, so pi plus and pi minus. And because they carry an electric charge, your magnetic nozzle can easily push them out of the way really, really quickly before they decay into high energy gamma. And this is a much better method, even though it's even more theoretical, because your delta V capabilities are essentially limitless. Your tank can store as much antimatter as you want, as long as you can make sure it doesn't touch the walls of the tank, because you have to also keep it magnetically suspended. So there's other engineering issues with this solution. Okay, the third solution is leave the engine at home. Leave the crew at home as well. Send a tiny chip, right, called a star chip, not to be confused with starship. A star chip that contains a power supply, contains a transmitter, and it contains a camera, so you can actually see where you're going. Attach that to a very thin layer of film, and that's going to create a solar sail. This solar sail is like a kite. You essentially, from Earth, blast 100 gigawatts of laser power at it and accelerate this craft, because the photons will physically bounce off it and transfer their momentum into it. And within 10 minutes, you will have accelerated up to 20% of the speed of light, having sustained an acceleration of 10,000 g. So you really couldn't have any other electronics or crew on here. They would instantly just die. And at 20% of the speed of light, you can send these things to Alpha Centauri in 20 years Earth time. Right? Now, what are the problems here? Well, this is not immune to the interstellar medium. It's a very thin sail. Think about what happens to a kite if you were to throw a rock at it or slice a needle through it or whatever. It's very susceptible to damage, and that's why you have to send so many of them. And the other problem is 100 gigawatts. 100 gigawatts of power per craft is a lot of power. Okay, we traveled interstellar space. The final frontier. We want to travel intergalactic. We want to really push the boundaries of how we can imagine travel in the future. So we're going intergalactic. Now, I'm sure a lot of you know about wormholes. I'm sure a lot of you have heard of wormholes. Essentially, this is a universal shortcut, pun intended. We can travel at 99% of the speed of light, but as you can see with the red path, it will still take us a certain amount of time to get there because we're traveling across space-time. But if we were to take the green path, which is going through a wormhole, we can essentially shorten that distance, which means for the same speed, we get there much, much quicker. Now, the problem with wormholes is so far, we haven't observed any in nature, and the math suggests that they're very unstable. So they'll be crushed really quickly, and they'll be crushed so quickly that even a photon can't go on the other side. The way to combat this issue, to keep the wormhole open so that your craft can go through, is the use of negative mass, or negative gravity as well. So you need an anti-gravitational force, and that anti-gravitational force will force the wormhole open because it will act against the gravitational force closing it, and your craft will be able to pass through in a much faster manner, right? So this is the classic thing of folding a piece of paper and putting a hole through it. This is 2D space, this animation, but the movie Interstellar used 3D space because that's what we live in, right? So 3D space plus time. So a wormhole was placed near Saturn, and if a hole in 2D space is a circle, then a hole in 3D space is a sphere, right? This sphere was 2 kilometers wide, and the reason it was placed next to Saturn is because if you place it next to the inner planets, it would have disturbed the orbits as well. And I'm assuming there's an assumption that can be made that placing a wormhole near Saturn, which is a fairly large body, wouldn't create those disturbing effects on the solar system that would lead to it being unstable. And this wormhole, which was designed by astrophysicist Kip Thorne, was designed such that it has a very smooth gravitational gradient. So as is characteristic with black holes, wormholes as well, if you had a normal wormhole, then you would be stretched really long as you enter the wormhole. It's called spaghettification. But with this specific wormhole, it was designed to have a gentler gradient so that the ship could pass through without being stretched. Now we get to the absolute limits. Space-time expands, right? Hubble's law shows that the further the space-time expands, and it expands in proportion to how far it is away from you. So if space-time expands, the further I look away from planet Earth, that means there is a point where space-time expands faster than the speed of light. This is called the cosmological event horizon, and this means that from that point in space-time that expands further away, that is moving further away from me than the speed of light, if a photon is fired in my direction, it won't ever get to me because the photon is traveling through space-time, which is moving further backward at the speed of light, faster than the speed of light. So to actually travel beyond the cosmological event horizon, you could use wormholes, but that again creates a new cosmological event horizon around the wormhole. Or instead of traveling through space, you could actually move space itself, so bend space-time. One of the best concepts we have so far of it is called the Alcubierre drive. So this is a form of faster than light travel that involves an insane amount of energy, and I'll talk about that in a bit. But the essential crux of this is we're surfing a gravitational wave we make. So if there are any surfers listening, this is essentially the most epic form of surfing there is, in theory. So this warp drive has a bubble, right? So this bubble, inside this bubble, space-time, local space-time is going to be completely flat. So you are stationary. My ship inside this bubble is stationary, which means I'm not experiencing the effects of time dilation. And that means if 1 year passes on my ship, 1 year passes on Earth, even though I'm moving faster than light. Then outside this bubble, just in front of it, we're going to crunch millions of kilometers of space-time all the way down to a few meters, right? And behind us, we're going to do the same, but except we're going to expand it. This essentially is how we create this gravitational wave to surf, and that pushes us forward. And the reason we can use this method to travel faster than light is because inside our bubble, we are perfectly stationary, so we're not breaking the speed limit, and space-time itself is pushing us. So relative to space-time, we're not traveling faster than light, but space-time itself is traveling faster than light, which is okay. Now, like I mentioned, Lorentz factor inside is going to be 1, no time dilation. And if we traveled all the way to Andromeda or even beyond in a week, exactly a week would have passed on Earth. And there are some practical limitations to this. What are the practical limitations? Well, wherever you go, you're going to destroy wherever you get. So because we're going to be moving faster than the speed of light and we're surfing a gravitational wave, think about surfing on water. If you were to surf forward, you're going to essentially be picking up all of the particles that are going with you. So you're picking up all the particles that are falling in that little crevice in front of you. And once you turn off the warp drive, once you've reached your destination, that insanely blue shifted amount of radiation and dust and whatever is going to be launched in front of you like a beam that's destroying everything. And it's going to have so much energy that if you, let's say I turned off my warp drive pointing at my destination planet and star system, it's going to basically be a beam that completely vaporizes both the planet and the star, and you came all that way for nothing. The second problem is the energy requirements. Firstly, you need anti-gravity to expand space behind you, because you can use an insane amount of gravity to compress space, but you need anti-gravity to expand space behind you. Secondly, you need negative energy, right? So this negative energy negative energy has been observed on the quantum scale, but in this case, you'd need the equivalent mass energy of the Voyager probes combined, which is like hundreds of kilograms versus just the quantum scale. And yeah, that's the problem with these drives. So now that we've officially reached the end of the universe, I'm going to open the floor up to questions, and I thank you for listening to me for the past hour and a half.
Thank you, Achal. It's amazing the amount of information that you and the graphics that you put into this presentation. Questions? I'm sure there must be many questions from you to Achal.
Irshad, go ahead.
Achal, can you hear me?
Yep.
Yes, we can.
I wanted to ask you on that anti-gravity keeping the wormholes open. Can we actually harness it?
I don't think there's any known form of anti-gravity yet, because yeah, there just isn't any known form yet. So we can't harness it because we haven't seen it experimentally or observationally. But that's not the case with like negative energy, where we've seen it, where we've observed it on the quantum scale, and we just need to figure out how to harness it.
But as the math say it's there.
Pardon?
Does the math say it's there?
I'm not actually too sure, because that was out of the scope of my research. But yeah, I really can't give you an answer on that, because it could and it couldn't. Yeah. Do we have any other questions? Yes. Terry.
You said that we need a lot of negative energy to make a warp drive work. So, like, are scientists close to making this work, or is it just like a theory for now?
For now, it is completely a theory. So originally, the bubble of the Alcubierre drive was a sphere, right? And it was calculated that using a sphere, the amount of negative energy you'd need would be the same as the mass of Jupiter, which is huge. And then eventually it was reworked. So instead of it being a sphere, it was a toroid, which is essentially a donut. And that reduced our energy requirements down to Voyager, the size of the Voyager probes. But again, it is still, it has basically the scope of this project has changed from something that would have never happened down to the scope of maybe in a few hundred years, it might be possible.
Okay, thank you, sir.
Any other questions?
Achal, you mentioned starships.
Yes.
Is that a reality? Is it in let's say the next 10 to 15 years? Could that be a reality?
Yes, technologically speaking, yes, it can be, because we have most of the technology we need already. The only issues I see with it actually coming into effect are, one, the ROI. Essentially, Breakthrough Starshot is the overarching project that is leading Starships, and I don't see much of a return on investment as of now with the current form of technology. But technologically speaking, it is feasible within the next decade or two. Yes.
Okay.
Yes. I don't know who raised their hand first.
I would like to ask a question. My question is, are any type of ships, rocket ships, going to make it through the wormhole, possibly through the next years from scientists, or could it not work because of the problems, like you said, of the photon, it cannot go through?
I think that's on the same level as of theory as the Alcubierre drives, maybe even more, because we I didn't research the requirements needed to create a wormhole. I just researched the requirements to keep a wormhole open. So firstly, that means we need a naturally occurring wormhole to already exist that we are going to keep open, or we can try harness and keep open. There's no observational evidence that wormholes exist so far, which means that essentially puts a rest to that for any time in the near future. So it's going to be hundreds beyond. I would bet money that we'll get to Alcubierre drives before we get to wormholes.
Okay, thank you.
Yes.
A question I wanted to ask. If I were to take a rocket ship, you said it would take a lot of resources and a lot of time to go out of the solar system. Would it be possible to take a rocket ship and use the sun's gravity to boost the rocket ship, maybe towards Jupiter's gravity, and then use Jupiter's gravity to boost us again to be able to go out of the atmosphere faster than normally?
Yeah, I mean that's what's been done. So you're describing a combination of the bioelectric transfer and gravitational assists. We have done gravitational assist already because that is arguably more efficient in this application. So the Voyager probes, all we did was launch them towards Jupiter. They flew by Jupiter. Jupiter gave them a gravity assist. Then they flew to Saturn. Saturn gave them a gravity assist. They flew to Uranus, and Uranus gave them a gravity assist to Neptune. And then after that, they flew by. Another craft to note is New Horizons. So what New Horizons did was it took a much more direct path. I'm sure it did a gravity assist somewhere. I don't remember where, but essentially it just brute forced it. So it used all of its rocket's fuel to push it all the way up to Pluto so that it could do a Pluto flyby. So I mean, yeah, there's both ends of that. With going down to the sun, I assume whilst that would be efficient as well because the bioelectric transfer does get efficient, the problem would be you would have the sun's atmosphere actually apply drag on you as well. And then there's the shielding you'd need because you're going so close to the sun, so heating effects also play a role.
Terry
Yes.
has a
Thank you.
question.
So theoretically, if we had advanced enough technology, would we be able to go through a wormhole and come back out with advanced enough technology, like just theoretically?
Yeah, if theoretically a wormhole did exist and we had a spacecraft that could traverse it, yes, you could traverse through it and then you could take a U-turn and come right back. Yes.
Okay, thank you.
I mean, that's what they did in Interstellar as well.
Terry, you have another question? Alexandra.
No.
My question would be about the super chip. So,
Mhm.
if the super chip, you said it would not work because it could be flammable. What if they made it very strong and it could possibly work? Do you think it would be possible as scientists to come together?
Okay, so I assume you're talking about Starship, not Superchip. Starship is the one that is the thing we're sending on sails interstellar. Yes, you could make the material stronger, but that's now a material sciences problem, right? So far we only have materials that are only so strong. So yes, we could develop materials that are effectively stronger and stronger and stronger for a very lightweight profile, and that could keep going until we eventually reach a point where yes, we could protect it using well, it could sustain such amounts of damage. The other thing I want to point out is the other method is inducing a gravitational field within the star chip. So it'll deflect all the interstellar dust, much like Earth's magnetosphere deflects solar wind. But that would increase the power supply requirements. And obviously, you'd have to have a lot of iron on that craft because the mass will increase so that you can generate a magnetic field.
Achal's contacts are here, and you could ask him further questions after you digest all the information that we heard. We will also be recording and putting up this recording on the ASB website. Achal, thank you very much for this presentation. It was very, very informative, and the graphics were just outstanding. Thank you very much. Have a good evening, everyone.